Standard enthalpy of formation is the change in enthalpy that accompanies the formation of 1 mole of compound from its elements with all substances in their standard states. Now, the point of standard enthalpies of formation is to set a standard by which change in energy, or in this case heat, can be measured. And the reason that the standard enthalpy of formation is used is because scientists can't really tell the amount of energy that is in a particular molecule. For example, cyclopentane. It doesn't really matter what molecule you use. Every molecule is going to have a particular energy associated with it. These bonds between these carbons, these sigma bonds, are going to have energy associated with them. These bonds between the carbon and the hydrogen is going to have energy associated with them. And in this case, there's going to be ring strain because the angles of the bonds are going to be depressed. They're going to be smaller than they should be. So there's going to be energy associated with this ring strain. And then, of course, there's even going to be energy associated with the protons and neutrons. When there's some kind of nuclear reaction, there's going to be a change in energy there as well. So all of this is difficult to measure. I don't even think they can measure it accurately. So in this case, in order to still have a method of getting useful information from changes in energy state, it's not necessary to know where the floor is really. For example, suppose I had two things at different heights. Suppose I had some object that was 10 feet up in the air. Oops. 10 feet up in the air, and I suppose I had another one that was 15. So the difference in height between these two objects is 5 feet. And the reason I know that is because I take 15 and I subtract it from 10. One is 10 feet up, one is 15 feet up. But suppose I don't know how high these are. Suppose there is no ground. I'm just floating in space or something, and I can't tell how far apart these two things are. What I can do is just set some arbitrary standard. I can measure from up here, I can measure from here, I can measure from here. But no matter where I pick my standard, these two objects are still going to be 5 feet apart. If I was 100 feet above it this way, then this would be minus 85 feet, and this would be minus 90 feet, and the difference would still be 5 feet. So this is essentially what scientists have done with standard enthalpies of formation. They have set some standard, and then from that standard, they are able to measure the distance of the distance from the object in question from the standard, and then they do it to the second object, and then they're able to compare the two because the standard is still the same. It's really the same as any other measurement. The reason I guess people are more comfortable with something like this is because the ground is a standard that they are using to measure, and they don't even realize that the ground is an arbitrary standard, but it just happens to be a very popular arbitrary standard. But it's no different as if we had taken the standard to be 695 feet in the air as opposed to the ground. The difference is the math would still work out to be the same. So they've defined this standard to be this. It's the state of compounds at 25 degrees Celsius and at 1 atmosphere. And there are a few other things for compounds. So here, standard gas state, form 1 atmosphere. Okay, we already know that. Condensed states, liquids, and solids are pure. They don't have anything else in them. Of course, that's not really going to be possible to do. There's always going to be some minor contaminants, but pure enough. Substances present in solution, the concentration is 1 molar. Okay. And then for elements, the form in which it exists at 1 atmosphere and at 25 degrees. So this applies to everything else. And what they mean by the form in which it exists is, for example, here's a standard formation, enthalpy of formation. Carbon, solid, this is how it exists at 25 degrees and 1 atmosphere, plus H2, well 2H2 really, and it's a gas, gives CH4, gas. And at room temperature, hydrogen, I don't know why that keeps happening. At room temperature, hydrogen exists as this, H2 gas. It doesn't exist as hydrogen with an electron missing. Hydrogen always bonds with itself, unless it's on a star or something like that. And then carbon exists in this large, like graphite-like network. But that's it. They stated it exists. It exists as a solid. So however it exists, mercury would be a liquid, and so on. So it's not, I guess, what people would think would just be the element by itself, like hydrogen with a missing electron, or carbon like this, or anything like that. It's just however, if I was just to take that element and then put it in a vacuum and just put it in a jar, however it's like at that state, at 1 atmosphere and 25 degrees Celsius, that is the standard state for that element. And this is how we're going to go about getting the standard enthalpies of formation. They take these elements, they react them, and then the enthalpy of formation. And this is the symbol for enthalpy of formation. H and then F for formation, and then this degree symbol means at the standard state. And usually people are going to be dealing with things at the standard state, but obviously in different areas of chemistry and physics, if they're studying the physics of, I don't know, something on a star or something else, that's not going to be so useful because nothing's going to be happening at 25 degrees in 1 atmosphere. It's going to be like 1 billion degrees and 1 billion atmospheres. So, but for most of the time in beginning chemistry, we're going to be talking about 25 degrees Celsius, 1 atmosphere. Unless something crazy happens. And the formation for this is, what was it? It was minus 75. Is that kilojoules? Yeah. Kilojoules per mole. And then once I have that, I can have some reaction where I have A plus B gives C plus D. And if one of these was like CH4 and then just other stuff, I would just take their enthalpies of formation and then I would use Hess's law and it just becomes just a regular problem. The only difference between this and the other stuff I've been talking about is just understanding what the standard is, what it means, why it's even there. It's because we don't know what the hell's going on. That's why it's there. And then just to think about it, I guess the way I always think about it is that each molecule has some definitive energy associated with it, but we just don't know what that is. And when I think of a reaction, I think of it in more of the reaction diagram. Let's say the products or the reactants have this much energy. This is just some scale. This is time. This is kilojoules per mole, whatever. If the products require less energy than the reactants, then what's going to happen is that there's going to be a minus delta H. And it should make sense. It means it's going to release energy. If I have some reactants and they require more energy to hold in that particular arrangement, with all the bonds, with the spare electrons, nuclear force, whatever, it doesn't matter, whatever reaction it is. If the products require less, that means there's going to be leftover energy. And what happens is that energy gets released as heat. That's basically what happens in these reactions. All these molecules require different amounts of energies to have them in that particular arrangement at a particular pressure and temperature. And if the products were to have more energy, then it would be an endothermic reaction. Then delta H would be positive. Because if I were to take all the energy used to make these molecules, it wouldn't be enough for the energy required for these products. So what happens is I have to put energy into this reaction. And that's kind of what an endothermic and exothermic reaction is. Exothermic reactions, the products had required less energy than the reactants. So the superfluous energy is just released as heat or through work or however it is in that particular case. And for an endothermic reaction, the products require more energy than the reactants. So energy has to be put into the reaction in order to give it the necessary energy to form that particular arrangement of matter.